Hello everyone, and welcome to the AI Research Roundup. I am your host, Alex. Today is May 11th, 2025. We're discussing an ICLR conference paper published just under 4 months ago, on January 22nd, titled Cybench, a framework for evaluating cybersecurity capabilities and risks of language models. This paper introduces Cybench, a system to see how well language model agents, AI systems that act based on language models, can autonomously find and exploit cybersecurity vulnerabilities. This is crucial for assessing cyber risks and for penetration testing, which involves simulated attacks to find system weaknesses. The framework uses capture the flag tasks. Think of them as cybersecurity puzzles for evaluation. So, to understand how Cybench actually works, this first figure provides a great overview. It shows the agent receiving a prompt, which includes the main task description, like capture the flag, and also specific subtask questions. The agent then formulates an action, say a command to run. This action is executed in a simulated environment, which is a Kali Linux system, a specialized operating system often used for cybersecurity testing. The environment then sends back an observation, and this loop continues until the agent submits its final answer, which is then evaluated. Alright. Building on that agent interaction loop, this table gives us a concrete example of those subtasks. It shows a specific capture the flag task called MOTP from a competition named HKCert. You see a series of questions like which file contains the OTP bypass vulnerability, essentially a weakness that lets someone get around a one-time password system, and then the agent's answer from a GPT-4o run and its evaluation. The final question is, what is the flag, which is the solution these agents are trying to find? This detailed breakdown into subtasks is really key for granular evaluation. Okay, so this next figure, figure 2, really zooms in on the agent's operational flow. You can see the agent starts with its memory, which is the initial prompt, plus a history of its previous responses and the observations it got back. Based on this memory, it formulates a structured response, including its reflections and plan, and then an action, like a command. This action is then executed in that Kali Linux environment. The environment returns an observation, essentially, what happened, and the agent updates its memory. This whole cycle then repeats, allowing the agent to learn. So building on how the agent formulates actions, Table 3 here shows the actual performance of models like Claude 3.5 Sonnet and GPT-4o. It compares them using different scaffolds, which are essentially varied structures for how the agent can issue commands, for example using a pseudo-terminal, a more interactive command line. We see unguided performance, how they fare alone, versus subtask-guided performance, with those helpful intermediate steps. First solve time, or FST, indicates task difficulty based on human solve times. For instance, Claude 3.5 Sonnet, using the pseudo-terminal, solved a task with a 2-hour, 3-minute first solve time when guided, showing these agents can tackle fairly complex challenges with the right support. Alright, moving on from those specific scaffolds, this table on page 8 gives us a broader look at the overall performance of 8 leading language models. We see metrics like unguided performance, so how they do on their own, and subtask-guided performance, with those helpful intermediate steps we talked about. For instance, without guidance, top models like Claude 3.5 Sonnet solve tasks with a first solve time up to 11 minutes. But with guidance, GPT-4o impressively tackles a task with a 52-minute first solve time. OpenAI o1 Preview also shows strong overall subtask completion, highlighting how guidance really boosts capability for these agents. Building on that idea of how guidance boosts capability, this figure on page 9, figure 3, visually confirms how task difficulty impacts success. On the left, for unguided performance, we see the number of models solving a task plotted against its first solve time, which is on a log scale, covering a wide range. There's a clear cluster of successes for tasks under about 11 minutes, with success dropping sharply beyond that. Then, on the right, with subtask-guided performance, more models solve tasks, and they can tackle slightly harder ones, though a limit remains. This visualization really underscores that 11-minute first solve time as a key difficulty threshold for unguided models. Okay, so drilling down even further, This extensive table from page 44 provides a task-by-task breakdown of model performance. For each capture the flag task, these are specific cybersecurity challenges. It lists the human first solve time, and then for each of the 8 models, like GPT-4o or Claude 3.5 Sonnet, we see a fraction. This fraction, say 3/5, shows how many subtasks the agent successfully completed out of the total for that challenge. The sum of scores at the very top aggregates these, giving an overall performance snapshot, highlighting models like OpenAI o1 Preview, which performed strongly across many tasks. So, stepping back from those detailed task-by-task scores, the Cybench framework itself offers a valuable open-source way to assess language model agents in cybersecurity. We've seen that while leading models can tackle professional capture-the-flag tasks, those specific cybersecurity challenges, especially if they take humans under about 11 minutes to solve, the truly complex problems requiring hours of expert human reasoning are still a major hurdle. It's clear there's much more development ahead. That's all for this AI Research Roundup. Thanks for tuning in.